Hi, in this video I'm going to give a brief introduction to FullControl GCode Designer. The buttons at the top here are how you interact with the software to call its functions. Over here in the green box you have settings about the overall printer. I've currently set them up to work for an automated 2. Down here there's some parameters that you can enter. I've left them blank for now. And in this section, this is where you'll enter the details about your design. So I'm going to add a line. I'm not going to go through all the details of these features in this video, they'll be covered in other ones, but that line is going to go from x50, y50, z0, and it's going to go in relative coordinates 50mm in the x, whilst not changing the y and z. And then I'm printing it with a width and a height of 0.4 and 0.2. So if I generate the G-code now, clicking that button at the top, it's copied the G-code to clipboard after inspecting this feature, and then I can paste that into a preview software. So I'm using Repetier Host, and there's my line going from the point 50-50 on this 10mm grid 50mm to the right. So now if I want to make a square, I'll need to print 50mm in the y and then negative x and negative y. So I'm going to add another line, and then I'm going to say it's going from relative coordinates 0 to 50 in the y, and then I'm going to have the same print settings. And then I'm going to copy that and just tell it to move in the negative x direction and then in the negative y direction. So that will complete our box or our square. And there's our square. So now to make that a box, I'm simply going to repeat that square 250 times. So I'll tell the software I want to repeat features 1 to 4, which are here. I don't want to change their x or y coordinates. The z coordinate I want to move by 0.2mm, and I want to do 250 repeats. And that will give us a G-code for a hollow box. And we can completely vary all the details we like about it: speed, extrusion width, layer height, number of repeats, overall diameter, overall width, anything we want. So now I'm going to show you an example of a more unusual structure. This is a figure from the journal paper, and I'm going to show you the top left, part A of the figure, that structure for calibrating strings. So in FullControl, I'm going to load this design which I've already created, and it's first printing a rectangle. That's what we were attaching the strings to in the figure, and then it's going to print strings across. So first prints a rectangle, then moves 5mm along the edge of the rectangle to begin the first string, and then these 5 features are going to print the first string. So I'm going to skip the rest and just show you the G-code for those first 5. So if I preview it in Rep Host, this is what it looks like. We've got our rectangle moved along by 5mm, and then we've moved up just a small amount, then moved across the structure, down, and then across to the beginning of the next string. So that was our 4 lines, moving up, moving across the structure, moving down, and then moving along to the beginning of the next string. And before doing any of that, we had this custom G-code line where it was combining these 4 cells to say extrude 1mm cubed of polymer. So now if I activate the next 5 features, they'll print an identical string coming back. So it will start at the end of that line, come up, across, down, and then to begin the next line. So now we've got a nice repeating structure. We're going to repeat 10 times in total in that direction. So we've got 20 strings being printed, and one of the nice things with FullControl is the ability to parametrically vary anything we want. So we could vary the speed of these, the temperature, how high we move each time, what I'm going to do is vary the custom G-code lines, so the amount of extrusion that's extruded before we start printing the string for each string, I'm going to gradually increase. We initially set it to 1, and what I'm going to say with this repeat rule is that every time we repeat this pair of strings, we're going to increase the extrusion by 0.5. So if I generate the G-code now, we won't be able to see this on the print path, but if we look at the G-code, we can see this value of extrusion. For the final line, it's 5.5, and the second last line before it, whereas for the previous pair of lines it was 5, for the previous pair of lines it was 4.5, so we've correctly changed our extrusion, so it's extruding 0.5 millimeters cubed more for each pair of lines. So then we can identify what's the best amount of extrusion to get nice consistent strings. So now I'm going to repeat this whole structure in the Y direction so that we have 10 copies of it in total. So I'm going to add a Cartesian repeat feature. We're going to repeat all of those features we just designed. We're going to displace by 0 in the X, 25 in the Y and 0 in the Z. 9 of them in 9 repeats gives 10 in total. So that G-code is then going to look like this. And we can see we've got this diagonal line as the nozzle moves from the end of one structure to the beginning. So I'm just going to add a line before the repeats to tell the nozzle to travel across the structure before we repeat all of that. So I'm going to add a line here before we do this repeat, and it's going to go from relative coordinates 0, 0, 0, so where the nozzle currently is, to 22 millimeters across the structure, and then we're going to tell it that it's traveling. The nozzle is travelling, so we don't need any information about the extrusion. And I just need to also include that new feature to say repeat that one, and that will now give us this structure. So we successfully moved across before moving to the start of the new one. And now for each of these repeats, let's change the speed. So we can do F speed, change the speed of the line that's going across to print the strings. So I'll put those details in here. So we're only going to edit feature number 5 and feature number 10. And we'll do it for all repeats, and then let's increase the speed by 500 each time we've got a new structure. So we'll be printing our strings at 10 different speeds for all the different structures. So if we won't be able to see it in the preview, but if we go up to the G-code, and in this specimen we've got an F speed of 10,000. If we go slightly earlier in the G-code, look at this specimen, we've got an F speed of 8,000. So for those strings going across, we've successfully changed the speed. So now we've got 10 different specimens, each with 10 different extrusion rates, and we've got 10 different speeds. So we've got 100 different unique combinations of parameters now for this structure. So if we repeated this column with four different temperatures in 4 different columns, we now have 4 different combinations of temperature, speed and extrusion rate, each printed for 2 strings, so we could identify what the best combination of print parameters is to print very neat strings. And this is only taking 3 minutes, so for that whole calibration print of 400 parameters it might take 10 to 20 minutes. And that's how we can achieve really nice printed structures where we've got strings down to 1/10 of the nozzle diameter, hundreds of them all being printed precisely. Now I'm going to show you the design of a practical component where the features are of the same size as the actual extruded filaments. And this is going to be a flow mixer for mixing 2 different fluids. A lot of the functionality that I'm going to show in FullControl will be related to this mathematical design figure in the paper, where we'll be using sinusoidal waves to fluctuate the geometry or the position of individual filaments. So this is the design. Initially I'm just going to create it for these 3 features. The top ones, we're going to have a circle of which we're describing everything about: the start position, the direction of printing, clockwise, anti-clockwise, the number of segments and its extrusion, width and height. We then have a line that's printing directly across that circle, and then we're going to repeat that for 150 layers. And this is what we'll have. So you can see every layer is identical, with just this 2 semicircles for 2 different flows. And now if I activate feature 4, this is going to rotate layers 1 to 50 by 1.8 degrees, which means over the 50 layers it will rotate by 90 degrees. So then the top 2/3 haven't changed, whereas the bottom third is now rotating. And then if I do the same for the middle section with feature 5 and the top section with feature 6, but we're just going to switch the direction of rotation, so the middle section is going to rotate clockwise instead of anti-clockwise, then we'll end up with this flow mixer. As we go through the layers, we'll see it going anti-clockwise, then clockwise, then anti-clockwise. And one aspect of this is we're going to have some bridging layers. So at this layer, we've got the line going across the structure is now being printed directly from the perimeter with nothing underneath it. So if that wasn't having a good connection with the sides, then we can just edit that layer, or we can edit that layer and then also the one here. So we could just say increase the length of that line to make it slightly overlap the perimeter to ensure we have a good connection. So the way I do this with feature 7 is we're going to say edit feature 2, which is our line going across, but only for the 51st and the 101st repeats. And what we're going to do is extend it by 0.4 millimeters in both directions. So now this line has been expanded slightly, and similar for the next crossover point. This line is also being extended. And just those 2 lines have been varied. Nothing else has been changed. And we could of course change their speed or their extrusion rates or whatever we wanted. FullControl will allow us to change any segment in the whole structure in any way we want, as long as it can be controlled through G-code. So now moving on to more geometric design. So what this feature is going to do, feature 8, is going to fluctuate our diameter. So that's generated the G-code. If I paste it in, we can see that's what it looks like now, where we're fluctuating the diameter. One simple feature is achieving that, and as we go up through the layers, you'll see them get wider, narrower, while we've still got our different rotations for our mixture sections. And another one, if I now skip that feature again, and this feature is going to create if we were say fitting this mixer in a tight fitting space and it had to deviate around existing components, then what this is going to do is just going to shift the each layer in the X direction slightly to the right and slightly back, so that we could say meander around an existing component, just like that. So this would be if we're trying to fit it around something that's going in the opposite direction here. And that's again very nice and smoothly done, so we're not going to affect our ability to have watertight printing if that's required, and we could vary that however we want as a kind of post-process to the design. So I'm going to skip that, and I'm going to add another section onto the top. So instead of just doing 150 layers, I'm now going to do 200. So we're going to keep the features that twist and rotate the bottom sections. So now we'll have the bottom section twisting, middle section twisting in the opposite direction, then twisting back, And then we're going to have a section at the top where we don't have any variation at all. And what we're going to do with this section is apply this feature 10. And what this is going to do is it's going to tell this point and this point to come towards one another, and it's going to tell this point and this point to move apart. So gradually this is going to transition from our circular shape into two separate circles. And that's what we've achieved. So then if I skim down through the layers, we'll see it gradually transitioning into those 2Ds. So this means we could have our two inlets connected, and then we have this smooth continuous transition into our flow mixture. And this was achieved by a very simple feature, just a sinusoidal function applying an offset to each layer. And then the final feature is going to say, if we wanted this structure to have an interface at an angle, then this is going to offset the layers slightly. So any segments of the print path to the right of the center point are going to move slightly higher, and any to the left are going to move slightly lower. This is in the Z direction, and it's only going to apply for this top section where we're having the split. And what that's going to result with is this structure. So we've now got our angle, and we've done this with non-planar layers. So if we zoom in here, you'll see our layers gradually transition from horizontal at the beginning of this section to be steeper and steeper and steeper until we get to the ultimate angle of our top surface. So this is just showing the wide range of designs you can come up with a very simple description of the design in FullControl. And this has got all the details about the print path, the speeds, the print settings. So if you were to produce this design and share it with someone, there is no chance for errors to be introduced if their slicer parameters are slightly different or anything like that. This is describing every single detail that will ultimately be sent to that printer. And compared to a CAD model and an STL file, it would be extremely difficult to design a CAD model with this type of detail, and you wouldn't actually have anywhere near the amount of information. So we wouldn't have be able to describe the order in which the lines are printed, the fact that we want these bridging ones to be slightly longer. If this top section wasn't printed in a non-planar format, then towards the top it would only be printing these top arcs and then have stringing in between and defects. So the CAD model would be much worse quality and actually very difficult to produce, and the STL file would be for some structures extremely large, whereas in FullControl you might describe all those details in less than a kilobyte of text data. And you can see more details in the paper about the production of some of these lattices with conformal cells and that sort of details that would again be very difficult or impossible for CAD to achieve. And please have a look at some of the other examples in the paper. This one is from a recent study where we're investigating how you can change the width of the extrusion by changing print parameters. So in this case we had 5 meshes which all had exactly the same print path, but we fluctuated speed to achieve graded pores. And this would be really important if you wanted to have the same print path to ensure perfect adhesion between different layers, but still wanted to have a graded structure, and this would allow you to do that. There's lots and lots of other things that FullControl can do. It's a very general software where really it's not constrained to a certain type of structure, it's just allowing you to design the print path, the G-code for whatever structure that may be. And it could be for small scale things for biomedical applications, it could be for concrete 3D printing, whatever the application, as long as it uses G-code, FullControl GCode Designer may be useful.